There are other structural information that we can derive from our knowledge of chemistry and electronic structure and molecular structure, which substances are more likely to fluoresce. Okay. This is another structure that we can think of. This is basically a fused ring structure. Two aromatic substances rings are fused here, and here it is one benzene ring and one pyrrole ring. Okay. So, fused ring structures now ordinarily fluoresce. Fusion of benzene rings to heterocyclic nucleus results in increase of molar absorptivity. Normally what you should expect is from molar absorptivity, if it is high, fluorescence also may be observed and it will be of high intensity only. For example, you can look at the structure of quinoline. See, there are two fused rings and all the bonds are conjugated. There is one nitrogen here. So, in isoquinoline the structure is different, slightly different, but again you can see that there are conjugated double bonds. Here there should have been one more bond here in between opposite to this bond or in conjugation with this bond. So, in the fused ring structures, all these kind of structures will fluoresce, and many more structures with 3 rings, 4 rings, 5 rings, definitely they will be having a probability of fluorescing. Okay. Then substitution on the benzene rings, this results in shifting of the lambda max and sometimes fluorescence is observed. So, if you have a lot of benzene rings in a given molecule and if there is substitution occurring, then fluorescence can be observed. Another possibility is substitution with halogens. Normally halogens are having large number of electrons and number of orbitals, and intersystem and conversions will be possible. So, the chances of fluorescence decreasing with fluorescence with halogens is quite large, and increasing intersystem crossing also to the triplet state. Now, in these are very simple examples of iodobenzene and nitrobenzene, and in such cases fluorescence always decreases. Sometimes we classify organic groups as a substitution of COOH functional groups, that acid, this is an acid group, this is a carbonyl group, this is an aldehyde group, and all these things on the aromatic ring inhibits the fluorescence. So, because these are all electron withdrawing groups. If there are electron releasing groups NH2, OH etc., the fluorescence will be, possibility of fluorescence will be much higher. Now, bridged compounds, these are known as bridge compounds, and then this is not fluorine, there is some other compound, I will tell you what it is later. So, bridged compounds and molecules with rigid structures fluoresce stronger than the non-rigid molecules. So, this is a biphenyl structure, very well known, this fluoresces, and here there is less fluorescence because the rings are all fused here in this case. So, lack of rigidity is another problem. Lack of rigidity increases internal conversion rate, and that results in a consequent increase in the radiationless deactivation, that is solvent solvent interaction, molecule solvent interaction, and then molecule molecule interaction also. There are 3 types of interactions where the collision will take place and the fluorescence decreases. And for example, there is one more possibility, that this is a, there is a nitrogen here, there is oxygen here, OH group is here. If I add a little bit of zinc to this, it forms a complex. So, once it forms the complex, again it gets bridged, and bridge compounds do not fluoresce as much as non-bridge compounds. So, in non-rigid molecules, part of the molecule can undergo frequency vibrations, and with respect to other parts, which may account for some energy loss, not all. So, other conclusions that we can derive from fluorescence is fluorescence normally decreases with increasing temperatures owing to the increased frequency of collisions causing deactivation by external conversion. This is a very simple phenomena, because as the temperature increases, molecules will start moving faster and faster, they gain kinetic energy, and once the kinetic energy of all the molecules is increased to very high level, then what happens is the collisions will increase and the fluorescence intensity will come down. Sometimes solvent viscosity, this I have already referred that use of polyvinyl alcohol, Thermax and other not Thermax, use of polyvinyl alcohol, glycerol and dextrose, maltose etc., they increase the viscosity. Viscosity increase means there will be less movement of the molecules. So, decrease in solvent in viscosity increases the probability of external conversion. This is a very logical conclusion we expect from increasing the viscosity. So, normally what we would like is the viscosity of the substance should be as less as possible in fluorescence measurements. Solutes and or solvents both containing heavy atoms decrease the fluorescence. This I have already shown you in the previous slide with zinc. So, such examples are carbon tetrabromide and other examples, ethyl iodide. The bromide is a heavy atom and iodide is heavy atom. So, if I add a little bit of ethyl tetrabromide or carbon tetrabromide, carbon tetrachloride, ethyl iodide etc., the fluorescence will reduce, because spin orbital interactions increase the rate of triplet formation, which results in reduced fluorescence. So, if a substance exhibits more resonance forms, it is very simple. Basically, whenever there is a resonance, we expect the molecules to stay in different forms which are in resonance with each other. That means, the electronic structure will be alternating between different structures without undergoing any change. So, the more resonance forms means the lower average energy of the molecule. So, this should normally increase in the fluorescence. So, that is what we are telling, number of double bonds, conjugated double bonds. If there are more conjugated double bonds, the fluorescence will increase. That is exactly what we are writing here. And sometimes pH is a very important parameter in most of the fluorescence methods. You increase the pH, sometimes it will increase in some type of chemicals, and you decrease the pH, sometimes fluorescence also will get destroyed. So, pH can act either way depending upon the structure of the molecule rather than the general conclusion. And the basic idea is, in colored molecules there is more resonance. In the non-colored leuco type of dyes, the fluorescence will die down. So, such substances are mainly organic dyes. They could be fluorescing in acidic medium as well as in fluorescence medium. So, those substances which fluoresce in acidic medium will not fluoresce in the basic medium, and vice versa also. Basic medium substances which are having highly resonating structures will get protonated, the functional groups will get protonated and the resonance structures will become less, the energy requirement will be high. So, fluorescence will decrease. Now, dissolved oxygen, another parameter. So, dissolved oxygen, what happens? It reduces the intensity of fluorescence due to photochemically induced oxidation. Normally, oxygen is a very corrosive substance, whether it is in the air or anywhere else. Pure oxygen is a corrosive substance. So, that is why God has created our environment. Air also diluted with about 80% nitrogen for us to breathe. If we were to breathe only pure oxygen all the time, most of our internal body parts would have been oxidized and destroyed in no time, and none of us would have survived. So, dissolved oxygen, what it does basically is it can photochemically induce oxidation in chemical systems. Not, I am not talking about the body systems. In chemical systems, if there is dissolved oxygen, it increases paramagnetism. It promotes the intersystem crossing and conversion of excited molecules. All these processes will result in the reduction of fluorescence. Basically, oxygen itself in aqueous, even if you have a system where there is no oxygen, but if it is an aqueous solution, you keep it open to the atmosphere, it will keep on dissolving oxygen from the air. So, all these it is very important in most of these spectrophotometric procedures that as well as fluorescence procedures, the oxygen, the system should be kept covered and there should not be much interaction with oxygen also. Similarly, other paramagnetic substances also will reduce the fluorescence. Reduction of fluorescence is normally referred to as quenching the fluorescence. So, what we understand from the discussion so far is fluorescence is a natural phenomena. It occurs in substances which are having resonance structures, and these resonance structures and fluorescence intensity is associated with pH, dissolved oxygen and several other paramagnetic substances and others, bridge compounds, etc. And the fluorescence procedure must take care of all these parameters which adversely affect the fluorescence. That is important for us to know. So, now we come to the practical aspects. The fluorescence, how do you quantify fluorescence? The quantum yield is a term defined for fluorescing substances, and or you can call it even quantum efficiency for fluorescence or phosphorescence, that is defined as the ratio of number of molecules that luminous to the total number of excited molecules. All the excited molecules need not result in fluorescence, as we have seen so far with a long discussion. So, the incidence of electromagnetic radiation on a molecule results in the number of molecules going to next higher energy level and then populating there. From there, the electrons have to come down to the lowest energy state and then cross over to ground state. So, during this ground state crossover, we have seen earlier that there will be number of molecules which are in the excited state, but all of them do not result in fluorescence. Lot of molecules will lose fluorescence by other means, which we have already discussed so far. So, the total number of molecules in the excited state to that of the total number of the substances which cause luminescence. That ratio is known as quantum yield or quantum efficiency. This is a very standard term denoted by phi for a compound that is determined by relative rate constants for the processes by which the lowest excited singlet state is deactivated. So, basically what we do is, it is a theoretical term defined to differentiate between the two phenomenon, but it also differentiates the excited singlet states and triplet states or deactivation, either way. So, how do we define fluorescence? In fluorescence, the quantum efficiency phi, we define it as number of parameters that cause the deactivation. So, in this equation you can see that phi is kf divided by lot of things like kf, ki, kec, kic, kpd and kd. What do these things mean is, f refers to fluorescence and I refers to intersystem crossing, EC is external conversion and internal conversion, and PD refers to pre-dissociation and KD refers to dissociation constant. All these terms are sort of equilibrium constants. So, it is the ratio of the equilibrium constants of all these to the number of excited molecules. Whenever the other things at the bottom at the denominator, that is Ki, Kec, Kic, Kpd and Kd are kept minimum, phi approaches unity. When all these other denominator systems are kept minimum, that means we can almost equate them to 0. Kf by Kf should be 1, because Ki, Kcc, all these things we can neglect with respect to Kf. So, in pure fluorescing systems or ideal systems, the maximum conversion rate you can get is 1 or 100%, whatever way you want to refer to that. So, it approaches unity whenever the other things are kept minimum. So, quantum efficiency for highly fluorescent molecules such as fluorescein approaches unity under certain circumstances. So, this fluorescein I had shown you earlier, this is fluorescein, there is a spelling error, but this I want you to remember that there is an error, and you can check up the good structure, proper structure in your textbooks, and the quantum field for a compound is determined by the relative rate constants by which the lowest excited singlet state is deactivated. So, this we have seen already, and fluorescein approaches unity. So, if the fluorescein approaches unity, then what we mean is, you take a compound of fluorescein, use it as a standard to compare other fluorescing systems. That is the beauty of fluorescein, because it approaches unity. That means, the intersystem crossing is less, and then external conversion is less, internal conversion is less, pre-dissociation is less, dissociation is less. So, why not we take it as a standard for fluorescence. Same thing is true even with quinoline, that also can be used as a standard for fluorescence measurements. So, how do we quantify the fluorescence? I was explaining to you that we should treat fluorescein or quinoline as a quinoline sulphate also you can try. All these things are having fluorescence efficiency as unity. So, the relationship of fluorescence with structure can be quantified by comparing with fluorescein or quinoline sulphate. So, this is an expression which we will be using quite over and over, and this relationship between fluorescence and concentration is similar to Beer-Lambert's law. So, what does Beer-Lambert's law say? It says concentration is proportional to absorbance, and when fluorescence intensity is unity, near unity, the concentration should be linear to, we replace the term absorbance by fluorescence. All other derivations essentially remain the same except for accounting the fluorescence efficiency, that we will see now. So, the fluorescent power, just like what we did in absorption spectrophotometry, is proportional to the number of molecules in the excited state, which in turn is proportional to the radiant power of the absorbed by the sample. This is understood very easily, there should not be any confusion regarding this. So, we can write the total fluorescence Pf, radiant power of fluorescence, must be a function of fluorescence efficiency, that is phi f, and related to the incident and emitted light, that is P naught by P. So, the energy difference P naught minus P is a function of Qf. If the Qf is 1, it will be 1, but if Qf is very less, the total fluorescence of the substance will be quite low. So, here P naught is the radiant power of the incident beam, and P is the radiant power of the emerging beam from the sample after it passes through the sample, and P naught minus P is the radiant power absorbed by the sample, it is not emitted. Now, the fluorescence efficiency is defined as the ratio of number of photons emitted as fluorescence to the number of photons absorbed. This way also we can define. Earlier we had defined that we defined fluorescence efficiency as number of total excited molecules to that of number of molecules resulting in fluorescence, that is by subtracting, by removing the intersystem crossings, etc., the other deactivation methods. Similarly, I can define in an instrumental analysis that the fluorescence efficiency is the ratio of the number of photons emitted as the fluorescence, because it is the emission one we are measuring, not the absorbance. So, to the number of photons absorbed, that ratio also I can take it as fluorescence efficiency. So, both of them should be essentially same if we consider the structure of the light, that is involving photons. So, I can write an expression something like this, that is the power of fluorescence emission is proportional to the radiant power of excitation beam that is absorbed by the system. So, I can write this equation, Pf is a function of quantum efficiency Qf, and then another proportionality constant, this we are introducing here, and P naught minus P, that is equal to K dash. I just put a simple constant because phi f is a constant, fluorescence efficiency is a constant, and K2 is a constant. So, combining this I have put it as K1 and P naught minus P remains the same. Now, what does Beer-Lambert's law say? P by P naught is equal to 10 to the power of minus epsilon Bc or ABC, where epsilon is the molar absorptivity of the fluorescing molecule and B is the path length and C is the concentration. This is what we have derived in Beer-Lambert's law. So, what I want to do is substituting the equation 3 in equation 2. So, I write fluorescence intensity. F is fluorescence intensity now, k dash into P 0 into minus into bracket 1 minus 10 to the power of epsilon B c. This is a very simple derivation resulting from the previous equation and the definition of absorbance. See, P by P naught is equal to 10 to the power of minus epsilon B c. So, if I take out P naught from this, I end up with an expression something like this, P naught and into bracket 1 minus 10 to the power of minus epsilon B c, because the P naught P is P naught into 10 to the power of minus epsilon B c. So, P naught is there in the second term also. I replace this P naught into 10 raised to minus E c, P naught I take it out of the bracket and I end up with an expression something like this, P naught into 1 to the power of minus 10 to the power of minus epsilon B c. Now, mathematically I can treat this as an exponential equation and expand it. There is a simple expansion process for this, that is known as Maclaurin series. You can look up your first year engineering mathematics or any mathematics book, and you can see that 1 minus e to the 10 to the power of x can be expanded something like this. Now, I put 10 to the power of minus b c as x, and then if I put it as x, I will be writing 1 minus 1 plus 2.303 into x minus 2.303 x square by 2 factorial and then x cube by 3 factorial, like that. So, I am going to put this 10 to the power of epsilon B c in the same equation and expand it according to Maclaurin series. This k 1 is here and then P naught is here. This I am expanding, 1 is here, and expansion of this is minus 1 plus 2 into 3.303 B c divided by factorial 1. I have not written because factorial 1 is 1 only, and 2.303 epsilon B c is factorial 2, factorial 3, like that. It is an unending series. So, in this equation 2.303 into epsilon B c absorbance, if it is less than 0.05, all the subsequent terms in this bracket, that is this one square terms and cube terms, if it is less than 0.05, you can square it, it will become 0025. If you can make it cube, 0.000125, like that, it becomes they become negligible. This 1 and 1 will cancel, and what we will be left with is 2.303 into k dash into epsilon B c into P naught. So, this equation, again this is constant, 2.303, this is constant, epsilon is constant. If I keep the P naught is constant and B is path length, if that is also constant, I have only the term fluorescence. I can relate it with a constant term and concentration. So, if this is a constant, it can be evaluated by plotting fluorescence versus concentration and determining the slope of the curve, provided it follows a linear response. So, equation 5 indicates, equation 6 also indicates a linear relationship of fluorescence with concentration as all other terms are constants. However, it holds true only if epsilon B c is very small. This condition holds true only for dilute solutions. We should never forget the fact that the dilution fluorescence is a phenomena which follows linear response only in dilute solutions, not in concentrated solutions. So, at higher concentration what happens? The relationship between fluorescent power and concentration becomes non-linear and reaches a value of P naught into QF. You can asymptotically, where there is no dependence on concentration. For example, if you go here, if the concentration is very high, then fluorescence will become constant. So, we can neglect the terms, and Pf would be P naught into Qf asymptotically, where there is no dependence upon concentration. This is a mathematical derivation of the fluorescence phenomena. So, actually what happens in the actual practice, the detector receives only a very small portion of the fluorescence emission depending upon the solid angle of the fluorescing radiation incident on it. The efficiency of the detector depends upon the fluorescence wavelength, that is G lambda. So, I can modify this equation 2.303 Qf into epsilon Bc, all other terms are constant, K into Bc, K represents the product of all other constants and B is the path length. A plot of concentration versus fluorescence should result in a straight line. This we have already seen, and linearity in fluorescence extends from 2 to 3 orders, that is 10 raised to minus 1 to 100 to 1000 concentration. So, a typical concentration fluorescence curve is shown here. You can see that at very low concentrations there is a standard gradual increase, almost linearity, but at higher concentrations 10 raised to minus 6, minus 5, minus 4, this is 2 orders, minus 6 to minus 4, and the moment it becomes minus 3, the fluorescence intensity will start decreasing. So, it is obvious that we should operate only in the region where there is linear response. So, this equation is interesting from two aspects. It shows that the sensitivity can be increased by working at very high excitation power to give large signal to noise ratios. Since the source intensity we can change from time to time, fluorescent signals cannot be measured in absolute terms. So, we need a standard. Therefore, all fluorescence measurements are made relative to reference standards of known concentration and corrected for background fluorescence. So, we will continue our discussion about this fluorescence, essentially to how we can adopt a fluorescence system into a Beer-Lambert's environment and see how we can determine different concentrations of the substances, parameters, water molecules, etc. in our next class. Thank you.